Every winter, like clockwork, people line up for their seasonal flu vaccine. But why is this an annual ritual when there are so many vaccines we just have to get a couple of times when we're kids? Welcome to IFL Science, The Big Questions. I'm your host, Laura Simmons, Health and Medicine Editor. And today we're talking one of my favourite topics, vaccines. Is it possible we could develop a one-and-done, universal flu vaccine that could protect us from any virus strain that may come along? To find out, I spoke with Dr Florian Krammer, Mount Sinai Professor in Vaccinology at the Icahn School of Medicine at Mount Sinai and Director of the Ignaz Semmelweis Institute Inter-University Institute for Infection Research, to learn more about the quest to produce one flu shot to rule them all. Dr Florian Krammer, thank you very much for joining me today. Why don't we start off by you just telling us a little bit about yourself and about the work that you do, if that's okay?
First, thanks for the invitation. So I'm working on the interface between virology, immunology, and vaccinology. And I do work on basic science, basic virology as well, but I'm very much into vaccine development. And one of my focuses is to work on vaccines that induce broad protection against influenza viruses. Some of them might be, some of these vaccines that I'm working on might be considered universal vaccines. Some might be more considered broadly protective. But that's kind of what I'm really interested in, figuring out what type of immune responses you need to get broad protection against viruses that change quite a bit. And then the other thing that I'm really interested in, designing vaccines that stop transmission, that stop basically transmission of the virus in the population.
So I think it's really clear from that intro exactly why you were the perfect person to speak to for today's episode of The Big Questions, because we are talking about whether we will ever see a universal flu vaccine, a truly universal flu vaccine. But we're going to cover all the sort of possible permutations of that and everything as we kind of go through. So I'm really excited to get into this. But first, maybe to start with, I think sort of roundabout now, or kind of in the last month or so in the southern hemisphere, and then around about sort of September, October in the northern hemisphere, we start to see the sort of campaigns and the adverts encouraging everybody to go and get their seasonal flu vaccine. So I wonder if we could start with just why we need to get one every year.
Yeah, that's a good question. And the answer is basically because the viruses change so much, right? So the vaccines that we use right now are actually pretty good vaccines. They induce neutralizing antibody responses against the strains that are in the vaccine. These responses are often pretty potent and they protect us. But the problem is influenza viruses are RNA viruses. They mutate quite a bit, right? When they replicate their genome, they don't have proofreading activity. So they make mistakes, they make errors. So mutations happen. And that, in addition to the immune pressure that we have in the population, because people have neutralizing antibodies that select for new variants, right? Similar to SARS-CoV-2 in a way also. And these new variants then escape these neutralizing antibodies. And so the viruses keep changing. And that's a big problem. And then it's further complicated by the fact that we have different types of influenza viruses that circulate in humans too, right? It's not just one virus, it's different subtypes. It's H1N1, H3N2, and then influenza B. So they always change, and that's the problem. And so when you get the annual vaccine, that's usually an updated version that is based on the newest information of what is circulating.
Yeah, I think sometimes we tend to forget that, don't we? Of like, as we just talk about the flu every year, but it's not just one flu, and they kind of have to get that cocktail of strains and variants right every time, or as close as they possibly can, to try to protect us as well as possible. Because as I remind people quite a lot in my role as health and medicine editor, I find myself, certainly every winter, I find myself writing a lot about why flu is not a disease you want to get. Like it's not just kind of the same as a bad cold. Like in general, it is something best avoided, I think. And if the vaccines can help us do that, then that's got to be a good thing. So we've talked a bit about, having to get the right combination of flu strains and kind of like knowing exactly how to formulate the vaccine every year. And I suppose this is a massive question, but how exactly do they do that? I have a vague recollection of being at university in a lecture and them talking about infecting eggs with flu vaccines, and I don't know if they still do that. But how exactly do they go about creating the right vaccine every year?
So basically, there's a lot of data collection. The WHO collects all that data from regional centers and from partner organizations. And so basically what they're looking for is they're looking for which viruses are circulating. They're looking for isolates. They're looking for sequences. And then they basically test these viruses that are circulating against panels of sera that were raised with vaccine strains and different other potential vaccine strains that they had in mind. And what you're looking for is if there is a drop in neutralizing antibody. It's a specific assay that measures what we call hemagglutination inhibition. So they called HI active antibodies, but it's basically a surrogate for neutralization. If you get a drop of the currently circulating viruses by a fourfold or more, then you would call that a mismatch, and that would tell you the vaccine is not going to work that well anymore, and last year's vaccine strains probably should be replaced. And then the vaccine is updated. It sounds kind of simple, but it's actually quite hard process, right? Because first of all, there's a lot of data. There's a lot of influenza circulation, and then even within one of these types of influenza, right, there's often subvariants. And you have to kind of almost predict which one will take over in the future, right? And so for the Northern Hemisphere, for the vaccine that would be used in Europe, basically the decision for next year's vaccine or for the next season's vaccine has to be made in February already, right? And so you have, of course, data of what is circulating until then, but basically you have to forecast. You have to try to figure out what might circulate in the next season. And that is the hard part. And sometimes the prediction, the forecast is wrong. The problem is that it takes quite some time to, once you have determined what should be in the vaccine, to actually make the vaccines, right? You have to get the right strains that can be produced. You have to produce them, you have to release them. There's a lot of administrative effort and a lot of development effort involved. And that's why it takes so long. And that's unfortunate, because during the time when the vaccine is produced, the viruses might change again, right? Specifically, we have the Southern Hemisphere season in between, right? That's in the summer of the European summer. And there's a lot of circulation in Australia and in parts of Africa and in South America. And that allows the virus to change there potentially. And then maybe what comes back to the Northern Hemisphere in fall and in winter might not be what was predicted to be there and what is now in the vaccine.
Yeah, I'm just picturing the vaccine scientists in sort of like May and June, kind of tentatively watching what's happening in the scenarios. Like, did we get it right? That must be really like stressful to wait and see kind of how good the predictions were every year. It's definitely not a perfect science, but it's kind of incredible that they do as well as they do, really, when you think about all the challenges involved in that. It's very, very impressive. We touched a little bit on why the flu is a particularly kind of tricky customer, in the sense of it has this tendency to mutate a lot, and there's a lot of, it's very sort of error prone in its replication. So that's why we need to keep doing this kind of dance of updating the vaccine, and we're sort of locked in this arms race with the virus to see if we can predict what it's going to do before it does it. I wonder if we could sort of talk a bit about how that's different from a lot of the other vaccine preventable diseases that we have, because there are, we have this big difference with the flu, where we have to go sort of every year to get a vaccine. But then with something like the MMR, for example, the recommendation, I think, is that you have 2 or 3 doses during childhood, and then you kind of set for most of your life. So kind of when we see these differences, I guess it's more to do with the viruses themselves than it is with the way we manufacture the vaccines, with the type of vaccines that we use.
Yeah, I think there's a bunch of aspects that you have to consider. I think the first one is, of course, that the virus mutates. But of course, other RNA viruses mutate too, right? Mumps, which is in the MMR vaccine, that's an RNA virus that mutates, right? Or it can mutate. But the other thing is way of transmission and where the virus actually replicates, right? So what we don't necessarily see with the current influenza vaccines is what we call sterilizing immunity, right? So when you get vaccinated, you get your flu vaccine in your arm. Typically, there's intranasal vaccines too, and that's a little bit different. But you get vaccinated, right? And then you make an antibody response and to a certain degree a T-cell response, and that's a systemic response, right? You get wonderful antibodies in your serum, you get circulating T-cells. The serum antibody protects the lung really well because it can get there. And so, it protects you from disease and specifically from severe disease. But the antibody that you get through injected vaccination is not very good at getting to the upper respiratory tract, right, to your nose. And that's actually where it's needed initially when an infection starts, right? And so what often happens is that people have immunity that protects them from symptomatic disease or from more severe disease, but not necessarily from infection. And so even with higher vaccination rates, and actually the vaccination rates are not high enough to even influence that much, the virus keeps circulating. And because it keeps circulating, it's really hard to stop, even if you are vaccinated, right? That allows it to continue to evolve, right? While with a lot of other diseases where we have vaccines, the vaccines stop the circulation. And that helps a lot because if you have less virus circulation or less circulation of a pathogen, it also cannot evolve that quickly, right? And so I think that's kind of a major difference, that it's really hard to deal with these respiratory pathogens. And honestly, we see exactly the same story with SARS-CoV-2 as well.
Right. Yeah, I was going to say that sounds quite familiar to, because that was a large part of the problem, I think, was, the vaccines are incredible and, without a doubt, change the course of the pandemic for the better. But there is that kind of niggly problem of they're not as effective at stopping transmission. They can protect you from getting very severe disease and indeed protect you from getting symptoms in a lot of cases, but they don't really have what we might have considered an ideal impact on transmission. So there's those sort of two sides to consider, isn't there? Are the nasal spray flu vaccines then better in that regard, in that respect? Because I think in the UK they're only offered to children. I'm not 100% sure, but they're definitely not as widespread as the intramuscular ones.
Yeah, so the problem is a little bit, the nasal spray is different, right? What we get injected is an inactivated virus.
Right.
The nasal spray is a live attenuated virus, so it's genetically weakened. And so that works well in kids. The virus is modified in a way that it replicates well at low temperature, right? And typically that means when you spray it in your nose, it replicates there because the temperature is lower, but it can't go down into your lung, which automatically protects you from getting disease from that vaccine, right? Which is really cool. It's a nice concept. And this works well in kids because they don't have a lot of immunity to influenza yet. And in order to trigger an immune response, the virus has to replicate in your nose. It has to actively replicate a little bit, right? Adults have a lot of pre-existing immunity already to influenza. And because this is a very weak virus, it basically doesn't allow the virus to replicate. And so in adults, it's not as good in inducing an immune response. But in my opinion, that live intranasal vaccine is better than the injected vaccine. It's just that, it's most useful in kids and not in adults.
That's fascinating. That's such an elegant system. I'd never really thought about how they just worked completely differently, but that's so elegant that it sort of replicates in the nose, but it just won't go any further down into the respiratory tract, which just sort of necessarily protects you from your disease. I love that. That's great to think about. So yeah, basically until for adults, essentially the story is going to be for the foreseeable future, we're going to have to go and get a top up of the vaccine every year if we want to be as protected as we can be against the currently circulating flu strains, except, and this is the sort of exciting unicorn on the horizon, is this idea of a universal flu vaccine, or as you said, a broadly protective vaccine that can cover sort of a broader range of strains and might mean that we don't have to do this annual ritual of getting a vaccine. So tell us, where are we on this? Because it sounds really exciting, but it also sounds a little bit like science fiction.
it's hard to develop these vaccines, right? There's a bunch of things that are hurdles, right? One is, so we talked about the need to update the current vaccines every year because the strains change. But there's a second reason why this needs to be updated. The immunity is relatively short-lived, right? And it wanes often within 6 to 12 months, right? And that's, of course, something that's also a problem. Even if you had a vaccine that gives you very broad protection, if the immunity wanes within 6 to 12 months, you would need to get annual booster doses too, right? It could be the same vaccine. It would need to be updated for new strains every year, but it would need to be given every year. And that's not a good solution, right? What you're looking for, what you would want to have is something that's similar to maybe the MMR vaccine, where you might give a bunch of doses to kids and then they're good for their life, right? That's ideal. That would be great. That might be hard to achieve, but people are trying to do that. And so I mentioned earlier broadly protective and universal influenza vaccines. I think there are differences in the definition, right? Broadly protective, for me at least, would mean that you have something that protects within a subtype, so maybe against all H1N1 viruses or all H3N2 viruses. But there's many different subtypes of influenza viruses out there in wild animal populations, specifically aquatic birds, right? We have now 19 different subtypes. Only 2 of them are in humans, right? H1 and H3. And the universal vaccine would target all of them. And that might not be important for seasonal influenza, right? Because if you get broad protection against the subtypes in humans, you should be good, right? But where do these viruses come from? They come from the animal reservoir. And every now and then, and the last time this happened in 2009, a virus from the animal reservoir jumps into humans and causes a new pandemic, right? And that's how H1N1 and H3N2 arrived in the human population. They jumped from animal reservoirs. And since there are so many subtypes out there, any subtype could do that. Right now, there's a lot of discussion about H5N1, right, causing trouble and potentially becoming a new pandemic. And so a universal vaccine would not just protect against H1N1 and H3N2 broadly, but also against all these other subtypes. That's the idea, and that's the difference between broadly protective versus universal. Where are we with those? There are really good approaches. There's different targets, right? There's some that would target more T-cell immunity, some that would be based on antibodies, some that kind of try both. And some of these approaches have been tested in clinical trials, mostly early clinical trials, to prove the concept that they work, that they induce the immune responses that you would want them to induce. But the problem is that most of them have not been tested in phase 3 clinical trials. That's late clinical testing, where you would actually see if they work in protecting you against disease, right? And so the problem is a little bit this bringing these vaccines from preclinical, so that's animal testing, and early clinical testing into this advanced development. And the problem with that is that it costs a ton of money. And so far, there is progress, and there has been a lot of progress in the last 10, 15 years, but it has been really a challenge to advance these vaccine candidates further than just early clinical trials.
Yeah, it's such a long process as well, isn't it? I think, we say, I quite often write about, a new drug is in phase 2 or phase 3 clinical trials. It's like that's, years of work has gone into even getting it to that point, and we're still not at the end of the road. I think, it's easy to underestimate just how long this process takes, but it would be amazing to see a kind of, even just like anything that would kind of change the face of how we vaccinate against flu, I think would be great. Just any sort of progress that's an improvement on the current scenario would be great. But we touched a little bit about, you mentioned about the strains sort of jumping from animals into the human population and how we've ended up with new strains and pandemic flu strains. I was slightly horrified when I was preparing for this episode. I was thinking back to the H1N1, the swine flu pandemic that everyone talks about. I was slightly horrified to realise that was like 15 years ago, over 15 years ago. I can't believe it's that long ago, because I remember that very, very distinctly. I remember listening to the radio. I was in high school at the time, and I remember listening to the radio, and they mentioned that there was this H1N1 strain of flu, and I thought, thought, oh, I wonder what that is. And then, of course, it sort of came careering into all of our lives. And yeah, more recently, there's a lot of sort of concern and chat about H5N1, particularly with it jumping into so many mammalian species. That is, a little bit worrying. I think I couldn't even begin to count how many stories I've written for IFL Science about H5N1 in the last few months, but it's definitely a hot topic, I think. So, yeah, I guess the dream would be to have a vaccine that could sort of give us that peace of mind for the seasonal flu that's going to come around every year regardless, and like a longer lasting immunity, but that also might put us in a better position maybe for when a new pandemic strain pops up, because it might not be H5N1. I mean, we talk about that a lot, but another strain could just do a totally unexpected mutation and come into the human population. I suppose it's not impossible, right?
No, I mean, there's plenty of candidates out there. I think H5N1 is a risk, and we should do everything to reduce that risk, which specifically in the US is not well addressed. But there's other viruses out there. Specifically, for me, a concern is H2N2. That's the subtype that caused the pandemic in 1957. So we know that this subtype can cause pandemics, and it circulated in humans from 57 until 68. So everybody born after 68 has no immunity to it. And that virus is actually not very prevalent in bird populations. But where it shows up is at live poultry markets in the northeast of the United States, including in live poultry markets in New York City every once in a while. And you can imagine that is not a good thing, because people go there, they buy live chickens, and these animals might have H2N2, and people might get infected. And, in a big city with a large population density, if you have a bunch of human infections, this might take off, right? So H2N2 is actually what I'm worried most about. But there's other things like H9, N2, H10 viruses, H7 viruses that cause zoonotic infections quite a bit, just haven't taken off yet, right? Any of those could mutate, and then there's also this mechanism that they can reassort, right? So influenza viruses have genomic segments, 8 of them, which you can imagine like chromosomes, right? And when 2 different influenza A viruses infect the same animal or the same human, and it comes to an infection of the same cell, they can exchange these genomic segments. And what happens there sometimes, and this is actually the mechanism behind the last few human pandemics, you get one virus that has new glycoproteins, a new hemagglutinin, a new neuraminidase, and then you have a co-infection with a virus that's very well adapted to replication in mammals or in humans. And then the replication machinery comes from that virus, and you end up with a virus that replicates well in humans, but our immune system doesn't recognize it. And that's usually what is a really, really dangerous situation. And that can happen in any zoonotic infection or any infections in mammals, right? With 2 different influenza viruses. And if one of them is H5N1, that would be a disaster.
Yeah, that's not a comfortable thought, is it? But it's absolutely true. We have to be, aware of the risk in that case. I think it's probably worth also at this point just mentioning, because you did just mention it, but we talk a lot about, H5N1 and all this, and people maybe don't know what the H and the N stand for, but the H is hemagglutinin and the N is neuraminidase, right? And they're surface proteins on the virus. I didn't realize there were so many types, though. I knew there were more than the ones that are just circulating in humans, but I didn't know there was. What is it about water birds that makes them such great reservoirs for the flu?
They're weird, right?
It's very unusual. Yeah, that and then obviously swine flu with pigs. I think we often think about pigs, but yeah, there's something about aquatic birds that they're harboring all these viruses that have the potential to jump into the human population and cause all sorts of problems, which we would ideally not see. The H2N2, that is really interesting. I was not aware that sort of crops up as often as it does in the US. That's kind of scary to think about. It sounds a little bit like the beginning of a horror movie. If anyone's any budding screenwriters are paying attention, that could be a good topic to explore. So that caused a human pandemic in the past, and then did that just kind of fizzle out naturally, and then the strain just kind of went away? Does that happen a lot with flu viruses?
Yeah, there's this very interesting dynamics of influenza viruses in humans, right? So in 1918, we had this H1N1 pandemic, right?
Yes. Yeah.
The estimates are that between 20 and 100 million people died. So pretty severe. And then that virus over time became a seasonal virus, right? So immunity built up in the population, put pressure on the virus. The virus started to change. We call this change antigenic drift. So it changed. And then this was circulating until 1957 when this H2N2 virus showed up in the human population. And as soon as H2N2 started to circulate, H1N1 disappeared. So it somehow competed it out. And that was very efficient. That just took a few months. And then in 1968, we had another pandemic with H3N2. So again, a different subtype. And that eliminated H2N2. And this is actually a very powerful mechanism, it seems, but we don't understand it completely, right? And then it doesn't seem to happen with all of these subtypes. So H3N2 was circulating in 1977 when H1N1 came back. But H1N1 didn't kick out H3 and 2, so somehow there's no crosstalk and no competition there. But then in 2009, when a different H1N1, the swine H1N1 jumped into humans, it eliminated the old H1N1 completely within months. So understanding these dynamics and understanding what happens there would be super interesting, because basically then maybe we could design interventions that use the same mechanism. And maybe we could eliminate influenza from the human population altogether, right? I think a lot about that. I don't understand it completely, and it might be multiple factors that come together in these elimination events, but it's super fascinating.
That is fascinating. I'm so glad you said that there, because I was going to come in and be like, oh, could we this is going to sound really sci-fi, but could we eliminate the flu? But yes, we actually maybe could. I have been vindicated by a proper scientist. That's very exciting to think about. Imagine that. But in the meantime, I guess the probably more likely prospect is an improved flu vaccine that's either broadly protective or, in a kind of hopeful dream world, maybe even a universal one. If I had to sort of be really cheeky and push you, what kind of timeline do you think we would be working on to see a sort of improved flu vaccine getting through that critical kind of phase 3 trial phase and maybe even getting into the clinic?
So again, there's good candidates out there. For some of them, there's early clinical data. So if you would have asked me, let's say a year ago, I would have been a little bit more positive about it. But these things take a lot of money. They take research funding, right? And so the funding situation in the United States is changing quite a bit. And that's the biggest funder in this space is actually the US government. And that might change. And I think that might have an impact and how fast these things could move. A year ago, we'd have said maybe, somewhere between 5 to 10 years, and we'll have something that looks good in a phase 3 trial. Now I'm not so sure anymore. On the other side, the European Union just started a campaign to promote the development of universal and broadly protected flu vaccine with vaccines with a substantial amount of money. So maybe, it's just the funding sources are just shifting a little bit. So we'll see. But I think I'm hopeful that in 5 to 10 years, we'll see something in a phase 3 trial that has potential. That doesn't mean that the trial is going to be successful in the end, but something that's at least as good that it is moved into a phase 3 trial. And I think there's plenty of candidates out there.
That's good. So it's not, it's a realistic prospect. It's hopefully coming down the road, and, a few more years to wait while we keep a very close eye on what H5N1 is doing and H2N2 and all this. I'm going to go away now and be ruminating on all of these potential flu strains. That's going to be a nice, comfortable evening for me. But yeah, so hopefully it's not a complete moonshot. It's going to be coming. We just may have to wait a few years to see it. I think to sort of close this out, one thing I would just like to ask is if there is anyone listening who is, at university, is studying virology at the minute, or is kind of wanting to get into health science or microbiology or anything along those lines, what would you recommend, or what advice would you give to any budding flu researchers of the future?
Well, if people are interested in virology and want to study that and want to do research, I would highly encourage them, right? We need young people in the field, and we need people with energy and fresh ideas to move the field forward. It's challenging times, I have to admit that, for research in general, specifically in the United States. It might be even more challenging for virologists, but I think it's worth to study these things. They are very important. We'll have viral pandemics again. We need people who deal with these problems. We need people who deal with virus infections in the population to make the situation better, to figure out things that we don't understand yet. There's a lot of things to learn. And there's a lot of things to then apply and to basically improve health of the population, right? We need people who do that. And this might not be the most attractive field right now. And it's certainly also not the field like cancer research, where potentially you could also, if you have the right dimensions, make a lot of money. But we desperately need young people to come and help us to solve these issues.
Dr. Florian Krammer, thank you very much for speaking to me today.
Thanks for the conversation.
The music and sound effects in this episode are credited to Audio Blocks and Pixabay.